Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we'll dive deep into Amazon DynamoDB Accelerator, or DAX, the fully managed in-memory caching service that can turbocharge your DynamoDB queries by reducing response times from milliseconds to microseconds. We'll explore how DAX works under the hood, walk through common caching patterns like cache hits and misses, and break down real-world architectures with detailed illustrations. Let's get started. Amazon DynamoDB is a fully managed NoSQL database service designed for applications requiring low latency, high throughput access to data. It supports both key-value and document-based data models, making it versatile for a wide range of workloads. Built for seamless scalability, DynamoDB automatically distributes data across multiple partitions based on a hashed partition key, allowing it to handle millions of requests per second without manual sharding. By default, DynamoDB provides eventual consistency, but applications can opt for strongly consistent reads when needed. It also supports ACID transactions, enabling multi-item, multi-table operations with transactional guarantees. The service offers two pricing models: on-demand mode, which automatically scales throughput as needed, and provisioned capacity mode, where developers can allocate read and write capacity based on the workload to optimize costs. To enhance query flexibility, DynamoDB supports global secondary indexes, GSIs, and local secondary indexes, LSIs, allowing applications to efficiently retrieve data using alternative access patterns. Additionally, DynamoDB streams capture real-time changes to table data, enabling event-driven architectures by integrating with AWS Lambda, Amazon Kinesis, or other services for change data capture, CDC, auditing, and analytics. Security is a core aspect of DynamoDB, with built-in AWS Identity and Access Management integration, encryption at rest using AWS KMS, VPC endpoints, and CloudTrail logging for auditability. It also complies with industry standards such as SOC, HIPAA, PCI DSS, and FedRAMP, making it suitable for highly regulated environments. Overall, DynamoDB is a powerful solution for applications requiring millisecond latency, automatic scaling, and seamless integration with AWS services, making it a preferred choice for high-performance workloads such as gaming, IoT, e-commerce, and real-time analytics. Amazon DynamoDB Accelerator (DAX) is a fully managed, in-memory caching solution designed to dramatically improve the read performance of DynamoDB. By leveraging in-memory data storage, DAX reduces query response times from milliseconds to microseconds, making it an ideal choice for applications requiring ultra-low latency access to frequently read data. One of the key advantages of DAX is its seamless integration with DynamoDB. Since DAX is API compatible with DynamoDB, applications can leverage its caching capabilities without requiring major code changes. Acting as an intermediary between the application and DynamoDB, DAX automatically caches frequently accessed data, reducing the number of direct reads from the database and significantly improving response times. DAX is particularly beneficial for read-heavy workloads such as gaming leaderboards, session storage, recommendation engines, and real-time analytics. It manages caching automatically by handling data population, eviction, and cache invalidation, ensuring that cached data remains relevant while minimizing unnecessary database queries. However, it is important to note that DAX primarily supports eventually consistent reads by default. While this enhances speed, applications requiring strongly consistent reads will need to bypass the cache and fetch data directly from DynamoDB. To provide high availability and fault tolerance, DAX operates as a multi-node cluster that replicates cached data across nodes, ensuring resilience against failures. The cluster-based architecture also supports automatic failover and load balancing, making it a robust solution for distributed applications. Beyond performance benefits, DAX can also help reduce costs by offloading read requests from DynamoDB, thereby decreasing the read capacity unit (RCU) consumption. This cost efficiency is particularly useful for applications with frequently accessed data, as it minimizes the need for expensive database read operations. However, DAX does not enhance write performance, making it less useful for write-heavy workloads. Applications with high write throughput may need additional optimizations, such as sharding or improved partition key strategies. By integrating DAX with DynamoDB, Organizations can achieve near instantaneous reads, lower costs, and scale their applications efficiently without the complexity of managing a separate caching layer. DynamoDB Accelerator, DAX, optimizes read performance through two distinct caching mechanisms, the item cache and the query cache. Each serves a unique purpose in reducing latency and offloading read requests from DynamoDB, helping applications achieve faster response times. The item cache is designed for storing individual items, making it ideal for operations that retrieve data using a primary key lookup. When applications use getItem or batch getItem requests, DAX checks the item cache first before querying DynamoDB, significantly reducing database round trips. One of the key advantages of this cache is that it ensures data freshness. Whenever an item is updated or deleted in DynamoDB, DAX automatically invalidates the corresponding cached entry to prevent stale reads. This makes the item cache particularly useful for high-throughput read scenarios such as user profiles, session data, or gaming leaderboards, where frequently accessed records need to be retrieved instantly. On the other hand, the query cache is designed to store query results rather than individual items. It is particularly beneficial for repetitive query workloads where the same filtering conditions or secondary index lookups are frequently executed. When applications use query or scan operations, DAX caches the entire result set, ensuring that subsequent identical queries are served from memory instead of hitting DynamoDB. However, unlike the item cache, the query cache follows an eventual consistency model, meaning cached query results may include stale data if the underlying records are updated in DynamoDB before the cache expires or is explicitly invalidated. This makes it well suited for analytics dashboards, leaderboard rankings, and product catalogs, where occasional data staleness is acceptable in exchange for faster performance. By leveraging both item cache and query cache, DAX optimizes different types of read access patterns, ensuring faster lookups and reduced operational costs. Let's walk through the sequence of events in both scenarios depicted in the illustration. One where there's a cache miss, and the other where there's a cache hit, using DynamoDB Accelerator, DAX. Let's take a deeper look at the cache miss scenario in DAX, which is a common occurrence when an item is being accessed for the first time or after its cache entry has expired or been evicted. The process begins when the application issues a read request to retrieve a specific item. Instead of contacting DynamoDB directly, the request is intercepted by DAX, which functions as a fully managed in-memory cache that sits in front of your DynamoDB table. DAX's first job is to check its internal cache to see if the requested item is already stored and available for immediate return. In this scenario, however, the item is not present in the cache. This is known as a cache miss. Since DAX cannot fulfill the request from memory, it transparently forwards the read request to DynamoDB itself. DynamoDB, in turn, retrieves the requested item from persistent storage, performs any necessary validations, such as access control or consistency checks, and returns the item back to the DAX cluster. Once DAX receives the response from DynamoDB, it performs two operations. One, it caches the item in its in-memory store so that subsequent requests for the same item can be served quickly. Two, it returns the item to the application, completing the read cycle. This approach significantly enhances performance for recurring queries. Even though the first request results in a cache miss and a round trip to the database, future requests for that item will be cache hits and served directly by DAX. Let's now explore the cache hit scenario in DAX, which represents the ideal performance path for read operations. In this case, the application initiates a read request, just as it would in any typical interaction. However, instead of going directly to DynamoDB, the request is routed to DAX, the in-memory caching layer designed to accelerate read-heavy workloads. This time, when DAX checks its cache, it finds the requested item already stored and readily available. This could be because the item was recently read from DynamoDB during a previous cache miss, or because it was preloaded into the cache by the application. Importantly, the item is still valid. It hasn't expired or been evicted. Because the data exists in memory and no validation with the underlying database is required, DAX instantly returns the item to the application. This bypasses any need to reach out to DynamoDB, effectively eliminating the latency and cost associated with a database call. This flow exemplifies the true strength of DAX. Performance is significantly improved, with sub-millisecond response times, making it ideal for low-latency applications like e-commerce platforms or gaming backends. Scalability is enhanced, as DAX offloads repetitive read operations from DynamoDB, ensuring that the database isn't overwhelmed with frequent access requests. Cost efficiency improves because no read capacity units, RCUs, are consumed from DynamoDB during a cache hit. For applications with high-frequency reads on popular items, this can result in substantial savings. Let's walk through the DAX write-through behavior, as illustrated here. When an application performs a write operation, whether it's a put item, update item, or delete item, the request is first sent to DAX, but instead of DAX acting independently, it immediately forwards the write to the underlying DynamoDB table. This ensures that the source of truth is always consistent and up to date in DynamoDB before any changes are reflected in the cache. Once DynamoDB successfully processes the write, DAX will then update its in-memory item cache to reflect the latest data. This guarantees that any subsequent reads for that item will return the updated value, minimizing latency for frequently accessed records. It's important to note that write-through only applies to the item cache, not the query cache. So while direct item reads will benefit from updated values in cache, broader query results still rely on DynamoDB and are not automatically updated or invalidated. Unlike some write optimization strategies, DAX does not perform write coalescing, meaning every write operation consumes capacity units in DynamoDB individually. This can lead to higher write throughput consumption, especially in write-heavy workloads. To maintain cache consistency across the DAX cluster, cache invalidation is automatically propagated to all DAX nodes, ensuring that stale data is not served from any node after a write. In summary, DAX write-through ensures strong consistency for item-level access patterns, improves performance for frequently read items, and keeps the cache in sync with DynamoDB at the cost of increased write capacity usage. It's a trade-off that favors read efficiency and cache freshness, making it ideal for applications where real-time access to updated data is critical. This illustration highlights the flexibility of Amazon DynamoDB Accelerator DAX when it comes to deployment configurations. DAX is designed to seamlessly support a wide range of application-to-table relationships, making it adaptable to different workload patterns and architectural needs. One-to-one configuration. In this scenario, a single application is integrated with a single DynamoDB table through one DAX cluster. This is the most straightforward setup and is ideal for isolated, purpose-built applications that manage a specific dataset. It offers simple caching logic, minimal configuration complexity, and is often used in microservices or single-tenant applications where the data model is tightly coupled to the application logic. One-to-many configuration. Here, one application connects to multiple DynamoDB tables via a single DAX cluster. This setup is useful when a single application manages diverse datasets, for example, user profiles, transactions, and activity logs, each stored in separate tables. With DAX in place, the application can benefit from low-latency access across all tables while centralizing cache management within one DAX cluster. Many-to-one configuration. In this case, multiple applications share access to a single DynamoDB table through a shared DAX cluster. This is common in scenarios where a shared data model is accessed by multiple services. For example, the user service and an analytics service, both querying a single user table. DAX provides a centralized caching layer, improving performance for all applications while reducing read pressure on the base table. Many-to-many configuration. Finally, we have the most flexible setup where multiple applications connect to multiple DynamoDB tables through one or more DAX clusters. This model suits complex, large-scale architectures such as enterprise systems or multi-tenant SaaS platforms where different modules or services interact with various datasets. With DAX, each application benefits from fast, in-memory responses across all relevant tables without sacrificing scalability or data separation. In summary, DAX offers powerful caching benefits across a wide spectrum of integration patterns, from simple one-to-one setups to complex many-to-many ecosystems. This flexibility allows you to optimize both performance and architecture based on your application's unique needs. Cache eviction in DynamoDB Accelerator, DAX, is managed through an automatic process that ensures efficient memory utilization while maintaining fast access to frequently used data. To optimize performance, DAX employs a least recently used (LRU) eviction policy, meaning that when the cache reaches its memory limit, the least recently accessed items are removed first to make room for new data. This approach ensures that frequently accessed records remain in cache while less used data is progressively evicted. A key aspect of DAX's cache management is automatic invalidation of stale data when updates or deletions occur in DynamoDB. For item cache, whenever an item is modified or deleted, its corresponding cache entry is immediately invalidated, ensuring that subsequent read requests retrieve the latest version from DynamoDB. However, the query cache behaves differently. Query results are not automatically updated when the underlying data changes, meaning applications may serve stale query results until they are naturally evicted or refreshed by a new query execution. Eviction also occurs due to memory constraints. If the DAX cluster does not have enough memory to store all frequently accessed data, older or less used entries are automatically removed. This can impact performance, as repeatedly evicted data must be reloaded from DynamoDB, potentially leading to temporary spikes in read requests and increased database load. DynamoDB Accelerator, DAX, supports time-to-live TTL and uses it to manage the cache, evicting items after a specified period, ensuring consistency with the underlying DynamoDB data store. In a multi-node DAX cluster, cache eviction happens independently on each node, meaning different nodes may retain or evict different sets of data based on local access patterns. This variance can lead to slight inconsistencies in cache state across nodes, though the overall system continues to function seamlessly. To minimize unnecessary evictions and maintain optimal performance, it is crucial to properly size the DAX cluster based on the application's data access patterns. If the cache is too small, frequent evictions can reduce the effectiveness of DAX, leading to higher read latency and increased database costs. By balancing cache size, eviction strategy, and read patterns, applications can maximize the benefits of DAX for low latency, high throughput workloads. When an item's TTL expires, DAX evicts it from the cache, ensuring that the next request for that item will be served by DynamoDB, refreshing the cache. DynamoDB Accelerator, DAX, provides two primary approaches to scaling. Scaling out involves adding more nodes to the DAX cluster, increasing the overall cache capacity and allowing the system to handle higher request volumes. This method is ideal for high-throughput applications where multiple requests need to be served in parallel with low latency. By distributing the load across multiple nodes, scale-out ensures better load balancing and fault tolerance, making it the preferred approach for large-scale and rapidly growing workloads. On the other hand, scale-up, vertical scaling, and scale-out, horizontal scaling. Scaling up involves increasing the capacity of existing DAX nodes by adding more CPU power and memory. This approach is beneficial when the current nodes are reaching their resource limits, such as high CPU utilization or memory exhaustion. It is particularly useful for applications with moderate workloads that require higher per-node performance rather than distributed scaling. DAX multi-node clusters support both scale-up and scale-out, automatically handling cache partitioning and load distribution as nodes are added or removed. To optimize performance and costs, auto-scaling can be configured to dynamically adjust the number of nodes based on workload demand. Metrics such as CPU utilization and request throughput help determine when additional nodes should be added or removed, ensuring efficient resource usage. Despite the flexibility of both scaling methods, there are practical limits to how much a DAX cluster can scale. If an application requires caching beyond DAX's scaling capabilities, alternative solutions such as Amazon Elasticache may be considered. Moreover, cost implications should be carefully evaluated. Scaling up increases per-node costs, while scaling out increases the total cluster cost. While DynamoDB Accelerator, DAX, can significantly improve the performance of read-heavy workloads, there are specific scenarios where DAX may not be the most suitable solution. One of the key limitations is for write-heavy workloads. Since DAX only accelerates read operations and does not reduce write latency, applications that require frequent writes with fewer read operations will not experience substantial benefits from DAX. In these cases, the added overhead of cache invalidation could lead to unnecessary complexity and little to no performance gain. Additionally, strongly consistent reads are not supported by DAX, as it only supports eventual consistency. Applications that demand strong consistency for every read operation, such as those requiring real-time data accuracy or highly transactional workloads, should bypass DAX and query DynamoDB directly to ensure consistency. Similarly, if an application has low latency write requirements, DAX will not help, as it does not optimize write operations. The write-through strategy employed by DAX means that write operations will still be directly applied to DynamoDB, and the cache will only be invalidated afterward, making it unsuitable for scenarios where immediate write performance is critical. DAX also works best with repetitive and predefined queries, so it may not be suitable for applications that perform dynamic or ad hoc queries. Since DAX caches specific query results, applications that require highly variable queries or complex filtering would not benefit as much, as each new or unique query would still require a fresh lookup from DynamoDB. Similarly, low read volumes or unpredictable access patterns would limit the effectiveness of DAX. If the data is not accessed frequently, or does not follow a predictable access pattern, the overhead of maintaining the cache would not justify the performance improvement. For small-scale applications, the cost of running a DAX cluster may outweigh the benefits, especially if the read volume is low. In such cases, solutions like DynamoDB's on-demand mode or in-memory caching systems like Redis or Elasticache might be more cost-effective and efficient alternatives. Lastly, DAX is not ideal for use with DynamoDB global tables. Since DAX does not support cross-region caching, applications relying on multi-region replication would not see the full benefits of caching across all regions. Similarly, for applications that deal with large query result sets, DAX may not be as effective, as it focuses on individual items and predefined queries. For complex data sets, tools like DynamoDB Streams with Amazon Athena or Redshift might provide better scalability and performance. Understanding these limitations helps ensure that DAX is used where it provides the most benefit, allowing applications to achieve the best performance while avoiding unnecessary costs or complexity. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.